this video we're looking to prove one of the properties we went through in yesterday's transpose video, and that is the one written at the top of the screen here. First of all, we're just going to write A and B in a form that's more easy to work with. So bear in mind for addition and subtraction, proof of subtraction, we could just put a plus or minus, then every step we could put a plus or minus, but we'll just leave that out for neatness. But for addition, the matrices have to be the same size, so that's something to remember. So this matrix A can be any size, but we have the A1 1th element, A1 second element, up to the A1 nth element. That's our amount of columns at n. Then we have our number of rows, m. Then all these dots, the individual dots don't represent elements, but there'll be elements between here. There could be 1, 2, 3, 4, 5, 6, 7, 8, whatever. And then in this bottom corner, our final element will be the AM nth element. B is defined almost identically. And the reason I'm just writing these in this sort of general way is so that this proof extends for matrices of all sizes. If I use like a specific matrix, say 3 by 3 or 2 by 2, then that only proves that it works for 2 by 2 matrix. And if I pick out specific numbers, then that doesn't really show anything, it just shows that it's true for the number. Right, so now we've got A and B, we can write out what A plus B is. And for matrices, we just add up the corresponding elements, so we get A11 plus B11, A12 plus B12, all the other additions up to A1n plus B1n. The additions in here, but I'm just writing down the key ones. A M1 plus B M1. There's all sorts going on here. And then finally A M N plus B M N. Okay, so that's our matrix A B. Now we want to take the transpose of that. So A plus B transposed. Basically, this first row becomes the first column. So we get A11 plus B11, A12 plus B12, all the way up to A1n plus B1n. This row would be, this column would become the first row, so the A11's already there, and we'd have all the elements that would be down here running all the way along to A M1 plus B M1. Now all these elements in the middle as well would be swapped round, and then finally we have AMN plus BMN, and that's because this one is in the last column and the last row, but if the last column becomes the last row, which it does in the transpose, this is still the last element, and vice versa, so that stays where it is. Anyway, draw a few more dots on here, right. But now this is equal to A11, A12, way down to A1N, AM1, AMN, all of that matrix added to B11, B12, B1N, fill in all these elements until BM1 down to BMN, and that's equal to A transpose plus B transpose. And why is this? Well, if you think back to our original matrices A and B, if we swap, if this first row becomes a column, we get A11, A12 to A1N. Well, that's what we've got. This element, AM1, goes up there. All the other elements swap around in the middle, and the same for B. So this is our final result here. Hopefully you understood this. It's a pretty simple little proof. It's just to get you into the idea of proof, how you have to speak in the generic case. You have to just put generic elements A1, A1, it doesn't matter what they are, and then you're trying to prove relationships between those things. Alright, so in the next video we're going to look at the other result to do with transposes, which was to do with multiplying them together. So I hope you come back tomorrow to see that video. If you did enjoy this one, please like and subscribe.